All right, let's go ahead and begin. I wanted to show you, I didn't realize you didn't have access to this, but you do now. So if you go to the lab, you can now see week 1. And okay, so of course it's not going to show up on this computer, but you should be able to see it on your computer. There's vodcasts there for a pre-lab lecture for lab 1 and for lab 2. So, I mean, they're only, maybe 5 minutes long, and it kind of goes over what you need to do for that lab if you have any questions. And you can see here, right below pre-lab or lab 1 pre-lab vodcasts, here is that worksheet, kind of like your data worksheet you need to fill out for that lab. And then here for lab 2, this is what you need to fill out, read through all of that for lab 2. And then lab 2 also has the lab report. So you're going to fill out this sheet down here, this one here, and then you're also going to do the lab report. And then the lab report, let's see, where did I put that? No. Okay, I'll need to post it on there. But it's under here. If you go under lab materials, yes, you can see this handout here. Here is your lab rubric, how everything's graded. So this is everything you'll need. So for the lab, you'll need, for example, a title page. And on that title page, I want course name and a lab title, date, the instructor, student names, and don't worry about the job part. Introduction, you see I want a background over the subject. So this one, lab 2, is over acids and bases. So, you might define, well, what is an acid? What is a base? Who discovered them? And just a brief background. Any references that you use, cite those. So if you, use your textbook or if you use a website, just let me know. And also put the purpose of the experiment. Why are you doing it? The next part, hypothesis. So it says use principles of science and topics learned in class to describe expected outcomes and likely error. So this one's over like pH and everything of acids and bases. So you might say, we'll learn a little bit about it today, so this might not fully make sense, but you could say like the hydrogen was bonded to an electronegative atom, making it more acidic, so you would predict based on its structure that the pH would be lower, okay, because lower pH corresponds to more acidic. Anyway, so basically say, if you think it's going to be, in this case, more basic or acidic, so higher pH, lower pH, and based off what? Okay, so your hypothesis. Experiment, that's basically the little worksheet you're going to fill out there, so just attach that with it. And the same thing here with data and quantities. Analysis, this is where you're going to explain your data, okay? What does it mean? So compare the calculations, just explain it. Overall, you have all these numbers and everything, and that's nice, but explain it to me. Conclusions, so basically summarize everything together. Tell me if you were correct in your hypothesis. Recommend any improvements. And the last thing is practical applications. So apply this to your everyday life. Why do you care about this lab? So the one we're going to do is acids and bases. Tell me how do they affect your life? Okay. And then of course you're graded a little bit on grammar and mechanics. Okay. So here's your references. Here's an example lab report. So if you want to see kind of what to expect, if you scroll down, and I made comments so you can see different things that I did in here. Here's an example of kind of what I'm looking for, so you have an idea. So that's so in addition to the worksheet for lab 2, you need to do the lab report. Oh yeah, let me go back to the main page. I'm going to post this in the lab because I just realized it's not in there yet. But right now, I'm in the class, the regular lecture, and I just went to lab materials. And it's the first thing here. Let me scroll up. It says lab materials, handout, and rubric. So it's the first thing listed there. Okay, so let's work out some questions. If you have any problems with lab or anything over the weekend, let me know, okay? And if you have trouble signing up for anything you need to sign up for, which would be Wiki, and again, you can have the same sign up for every single person in your group, okay? If you don't want to do like 4 different sign-ins, I don't care how you do that. And then Sapling would be the other one that you need to sign in for. So start those. There is sort of a, what do they call it, like a practice thing on Sapling. And if you do that, I will give you bonus points for doing that because it will help you. I don't know if it's actually organic molecules that you're drawing, but they'll have you practice drawing and give you tips on it. And if you go through that, it should help you through the rest of the homework, so it'll make everything go smoother for you. So if anything, think of that as some extra points. Or I told you the whole entire class is based off points, and so those are bonus points you can get. So work on that if you have time. Okay, so we looked over bonding, I think was what we looked over yesterday. We stopped about right there. Okay, so we have protons and neutrons in the nucleus of the atom, which make up most of the mass. Okay? Protons distinguish the type of atom, and electrons are involved in bonding. So we went a little bit further into bonding, and we looked at electron configurations. Let's practice. This is just from worksheet 1.1, but I'll put up what it is. The electron configuration for chlorine. So we want to do the electron configuration and the electron diagram. So here's chlorine. And let's go ahead and do the noble gas configuration, because that's more than likely what you will be using. So let me pull my periodic table out. Okay, so you can't see it. Chlorine is right here. So what do I write down for the electron configuration? What's my noble gas I'll use? Neon, so the one above it. Then I follow over, so here's neon, then I start right here, which is 3s2. And then move over a little more. And this is 3p5. Okay, and if I'm doing the electron diagram, which is where you draw the arrows, so I look at the S, how many lines do I draw for S? 1, because there's only one S shape, and then P, 3. 1, 2, 3. So for the S, I have 2 electrons. How will they look? 1 up, 1 down. And then for the P's, 3 down, or 3 up, 2 down, 1 unpaired. So these are just different ways to represent the electrons in chlorine. Because it's important to know what electrons you have. So our valence electrons, we have 2 s electrons in the 3rd level, and we have 5 p electrons in the 3rd level. And we can see that one of those electrons is unpaired, which would be the most reactive of the electrons. Okay, then we also looked at Lewis dot structures. So if we practice, let's do this first one, NO3H. So this is actually showing you bonding, So this is sort of our first bonding representation. So which atom out of all of these will be our central atom? Nitrogen. And this hydrogen, what is it bonded to? One of the oxygens. So I'm going to bond all of my oxygens with single bonds. Okay? And then my hydrogen, I'm going to put on one of the oxygens. Does it matter which one? No. I'm just going to put mine right here. Okay, so let's look at this oxygen here. Is it happy? Yes. The more electronegative? Uh-huh. No, you want the least electronegative as the central atom. With the exception of hydrogen. So the furthest away from fluorine will be your central atom, except hydrogen. And that's why hydrogen's not, because it's technically further away from nitrogen. Okay, so how many more electrons does this oxygen want? 4. It has 1, 2, 3, 4 that is sharing right now. So it wants 4 more. So I'm going to do 1, 2, 3, 4. Well, 1, 2. Yeah, it's sharing these two, but I'm saying counting the total number of shared together would be 4. So it's contributing these two to the bonds, but total sharing, looking at all of them, is 4. So now we have 8. Now what about this oxygen here? How many more does it want? 6. So we'll pair those up to make 6. And what about that last one there? 3 more. Okay, and that's actually all the electrons that you have. Okay, we've made everything happy, but we never checked nitrogen. Does it have the 8 electrons around it? No, it doesn't. So what do we need to do here? Double bond. Where are we going to make a double bond between? Oxygen and nitrogen. You're going to choose either one of these two oxygens. The reason it's these two and not that one, because these have more electrons around them, so they're more readily available. So you could have chosen the right or the left one. Okay, I'm just going to choose this one. Move those electrons over. All right, now the last thing I want to do is check the formal charges. Is hydrogen happy with just a bond? Yes. If hydrogen just has a bond, which is what it will always have, the formal charge is always 0. Okay. And now let's look at this oxygen right here. Let's call this one oxygen 1, 2, 3, just to distinguish between them. So oxygen number 1. How many valence electrons does it have, or should it have? 6. And how many is it actually using, contributing? 6. 1, 2, 3, 4, 5, 6. So formal charge is 0. Let's look at oxygen 3. So again, the valence electron should be 6. And how many do you count that is actually contributing? 6 again. 1, 2, 3, 4, 5, 6. Oxygen 2 should be 6 again. But what do you count? 7. 1, 2, 3, 4, 5, 6, 7. which gives us a -1. And then if we look at nitrogen, it should have how many? 5, because it's in group 5. And how many is it using? 4. Just 1, 2, 3, 4. Which gives us a +1. So nitrogen has a +1 formal charge, and this oxygen number 2 has a -1. Now if we look at the overall charge, if we add -1 to +1, what is it overall? 0. So you see here, this NO3H, it doesn't even show a charge because overall it's 0. All right, let's practice another one of these. Okay, write this one down. Okay, and work kind of in a group and see if you can figure this out. You know, the person next to you, whatever, you know, discuss, and then we'll check it here in a second. All right, okay, so let's check this. So how many carbons are bonded in a row? 5. So I'm going to do 1, 2, 3, 4, 5, and then what's at the end? Nitrogen. The first carbon has how many hydrogens? 2. The next one? 1, 2, 2, 0. Okay? So now we check. What's the magic number for carbon? 4. Is this one happy? No. The one next to it? No. So what do we put there? Double bond. What about this one? That one's good. This one? Yes. That one? No. What do you need? A triple bond. And then nitrogen, does it need anything else? A lone pair. All right, so remember, check oxygen nitrogen and any of your halogens for lone pairs, because they're pretty much always going to have them, okay? So always check those out. Okay, so this leads us into a concept called dipole moment. Okay. Remember, we have electronegative atoms, and electronegative atoms are atoms that are attracted to electrons. Okay? They want electrons closer to them. Okay? So here's a structure right here. Now, if we're looking at, let's say, carbon versus chlorine, which one is more electronegative? Chlorine. Remember, the closer you are to fluorine, the more electronegative you are. Okay, and chlorine's right below it. Okay, so chlorine would be the most electronegative. So do you see this sign right here? This is a delta. This is a partial negative, meaning that's your electronegative atom. Okay, and then right here on carbon, because we're looking at this bond right here, would be considered the partial positive compared to chlorine. Okay. So I always have to tell you which bond we're looking at. In this case, carbon-chlorine. And then you have to tell me which one's the most electronegative, and you put your partial negative there, and which one's the partial positive, which would be the least electronegative. Okay? There's energy associated with this. Okay? So you have this dipole moment, and that's basically what they call the energy associated with it, because the chlorine's pulling those electrons towards it. So when we draw this, we have this right here, and when we draw this, we kind of show the electrons, equal length apart. But that's not actually fully correct, because chlorine is so attracted to electrons, it's pulling those electrons towards it. So really, it's more like this or something. So there's still a bond there, but do you see those electrons are a lot closer to chlorine than they are to carbon, because chlorine is attracted to and pulling those electrons towards it. Okay? And that energy associated with pulling those electrons towards it, because it's electronegative, is called a dipole moment. Okay, it's called a dipole. Now, if you want to, so you put your partial positive there, partial negative there. And then if you want to say the direction of the dipole, you would say it's going towards chlorine. So when you draw an arrow. That means it's going that way, the pull. And you kind of put this sort of like a plus sign over carbon, saying that they're coming from carbon. So it's that partial positive there. So you have, it's the direction of the dipole is towards chlorine. Now this is important for bonding because these electrons aren't actually shared exactly perfect. This causes, like that dipole I was talking about, it causes a mismatch in energy there. So it makes, especially this carbon right here, reactive. Okay? It has this partial positive, and so it wants to react further. Okay? So we'll go over this when we start looking at bonding and reactions and everything. But you'll find that anytime you have an electronegative atom bonded to carbon, that's going to cause reactivity. Okay? So if you're having, looking at biochemistry, the molecules in there are huge. Okay? So you might not know what this all means. I'm making something up, so don't take this to heart. Okay, but do you see, let me draw something right here, OH, okay? Oxygen is very electronegative. It's very close to fluorine, okay? So the bond that's reactive on this whole entire thing here is this bond right here, the bond with the electronegative atom. Okay, so that can become important if you want to know, okay, I have this huge molecule, where in the world will it react? Okay, it will react where that polar bond is, where you have that electronegative atom attached there. Okay, again, because this atom's pulling the electrons towards it, it makes this bond not equally balanced. Okay, so it's unbalanced, so there's reactivity there. Okay, don't worry about that. Resonance. Okay, so this can be a difficult topic, and I'll try to hopefully go over this well enough where you won't have too much trouble. Okay? Do you remember when we were doing like multiple bonds in a structure? So we just did NO3H, and the original, I'll just draw this really fast. Okay, so we originally had this, right? But we said nitrogen wasn't stable yet, right? We needed to move electrons over, okay? When we actually moved electrons over like that, that was resonance without you realizing it, okay? So resonance is moving electrons in order to stabilize an atom. Okay, that's sort of the definition of it. So do you see that I moved electrons to stabilize nitrogen? Okay, so if you ever want to know why does something resonate, I get that question a lot, it's because it stabilizes an atom. Not necessarily. So we'll do a lot of examples I'll show you. But just by definition, if you move electrons around, you're doing resonance. Okay, so now you need to know what can you move around. So I'm saying electrons. Electrons is pretty broad. So lone pairs, do you see we can move lone pairs? That's what I moved right here. And you can also move double bonds and triple bonds. You cannot move a single bond. Let's look at that. Because these bonds are made up of electrons, right? Okay? So in theory, you can move them. But if you see here, if I move this bond, so these electrons making of this bond, if I move them, let's say all on oxygen. Okay? Do you see this bond is broken now? And so you would have this oxygen atom kind of in space, away from everything else, right? Because I moved, it's not sharing anymore, I moved them onto oxygen. So that's why you cannot move single bonds, because it actually breaks the connectivity of your whole structure. So you have to keep the integrity of the structure, okay? So this nitrogen still has to be connected to this oxygen, and this oxygen. But the one thing that can change is how many times it's connected. So you can go from a single to a double bond, okay? So do you see if I put a double bond there, is that nitrogen still connected to the oxygen? Yeah, it's just connected with a stronger bond, okay? So you can't move single bonds, but you pretty much can move everything else. So let's practice this. The more you do it, the easier it becomes. And there's rules to these, so let me tell you the rules. Okay, you want as many, to make a resonance form ideal, like to make it the best possible, you want as many octets as possible. Okay, so remember when we had 8 electrons around it? Remember that was ideal? Okay, that's what you want. You want everything to have the 8 electrons. Has least amount of charges. Okay, so you know the formal charges we calculated? So if you have one that has 3 formal charges versus one that has 0 formal charges, the one with 0 is more stable. Here it says has the negative charge on the most electronegative atom. So remember, electronegative atoms love electrons, right? So they want more electrons. So if you have a negative charge, you have more electrons, okay? So you want the electronegative atom to have the negative charge, if you have to have a formal charge. Now obviously, if you can make it 0, that's the best. But if you can't avoid it, then the electronegative atom likes the negative charge. And then there's this one here, which hardly ever comes up, but just in case it does randomly in your life. Charge separation. So let's say we have a positive and negative. It's more stable when they're close together. Okay, so let's say I have a molecule as long as my arm length. Okay, so if I have the positive over here, the negative over here, they're pretty far away. But what if I have the positive here and the negative here? Do you see they're closer, so they can stabilize each other better? Okay, so it's just literally distance. Okay, so those are the rules. I hate just like saying rules because they don't mean much to you until you put them in practice. So let's practice them now. So let's start with an easy one here. Okay, and let me go ahead and put the formal charges here. Oops. So then -1, and that's a positive. Now for resonance, I want to stabilize this. Do you see that this carbon does not have the 4 bonds to it, right? So is that very stable? No. And I see I have 2 formal charges in there, and I would prefer to have 0 if I can. Okay? So to draw the other resonance form of it, okay, what would I do? What do I want to move? The electrons, which ones? The lone pair? To make a double bond right there, right? Just kind of like what we've been doing. So if I draw that, okay, so let's see here. This carbon here had a positive charge. Is there a positive charge here anymore? No, because you see how it has the 4 bonds, so the formal charge is 0. What about oxygen? How many valence electrons should it use? 6, and how many is it using? 6, so the formal charge is now 0. So do I have any formal charges? No. So if I'm comparing these 2 structures, which one is the best? The one on the right, okay? Now in your homework, if I remember correctly, what they do, and it varies from problem to problem, but they might have both of these structures and they say draw the arrows, okay? So do you see, to go from this structure to this one, we just draw that arrow right there, okay? Now what if I want to go back? What if I want to make this structure into that one? What do you do? Draw the arrow going up, right? It's just the reverse. You see how it's going down here? So that means this one's going to be going up, okay? And both of these are resonance forms. Now this one's better than that one, but they both technically exist, okay? Resonance, these forms are like hybrids of each other, okay? So yes, probably 99.9% of the time, the structure will look like this. But that small percent of the chance it is in this one here. So they do, all resonance forms do exist, okay? But some are better than others, okay? So these are the 2 resonance forms of this structure, okay? Another thing, I know this one is easier because you could just see to move it down, but one thing that could help you is that if you have a negative in the structure, you're going to start there, because that's where all of your electrons are, so it's easier to move those. So if you have a negative, start there and move away from it. So let's look at another one. And let's see if we can figure this one out. This one's going to be a little bit harder. Okay, so the first thing you should look at is, do any of the atoms not have an octet? Okay? They're all stable, right? In the sense that they have 8 electrons around them. So did that help us at all? No, not really. Okay? So what we do, remember I told you the rule, if you have a negative, start there. Okay? So I'm starting right here. Now on this oxygen, which has the negative, what can I move? Can I move the single bond? No. But what about the lone pairs? Yes. Okay? So let's move, when I have a lone pair, I pretty much usually just move it to become a bond, to double bond in this case. Okay? But let's look at that. What did I just do here? Now, ignore my arrow for 1 second. How many bonds does carbon have right now? 4. Does it want another bond? Can it even have another bond? No. So carbon says, what are you doing? Get away. Okay? So we need to move something away because it's not going to accept this. Okay? So what can I move on carbon? One of the triple bonds. Okay? And where am I going to move that to? On nitrogen, and it will become a lone pair. Okay? Now we drew our arrows. Now let's see the consequence of those arrows. Okay? So let me just do N, C, O. So that's the basic structure there. Now oxygen, how is it bonded to carbon? How many? 2 bonds. And how many lone pairs on this? 2. Okay, now carbon to nitrogen, how many bonds there? 2. And how many lone pairs on nitrogen? 2. Okay, now let's check our formal charges. Anytime we move electrons, we can change the formal charge. Okay, carbon, will it have a formal charge? No, because it has 4 bonds. Oxygen should have 6, right? How many do we count? 6, so that one's good. Nitrogen should have 5. What does it have? 6, so that would make it a -1. All right, now comparing these two here, which one would be better? They all have octets. You can check it if you don't believe me, but they do. So what's different between them? The lone pairs, and what did it do with the lone pairs? If we look at the formal charges, over here the formal charge, the -1 is on oxygen, and over here it's on nitrogen. Which would it prefer to be on? Oxygen. Why? Because it's more electronegative. Okay? So you want your negative charge on the most electronegative atom. Okay? That's a really common thing that comes up. So either you're usually looking at an octet rule, or where the negative charge is located, and then the final one that comes up quite a bit also would be the number of formal charges. So this one is the best. Let's draw the arrows going backwards. Let's say we want to go back to this one. Okay? So if I start with this lone pair, to go to this structure, where do I move the arrow? Yeah, to the right to become a triple bond. Do you see that here I have a triple bond, but here I have a double bond. So I need to move that over to become a triple bond. Now what about right here? I have a single bond, right? Now what do I have right here? Double bond. So where do I need to move this? Right again, onto oxygen. Do you see the arrows chase each other? They chase. They never meet, okay? So that will always happen. So if you ever draw your arrows and they come together, for some reason I do this. You see how these arrows would meet together? If you ever do that with resonance, you did it wrong. Okay? They'll always chase each other. So that will kind of help you too, to give you a hint. when you're doing these on the homework, they're very, very specific, which can be great, but also they can make you pull your hair out, for real. Okay? So, for example, this lone pair, you have to make this lone pair highlight blue when you put your cursor over it, and you see you're moving it to become a bond. Okay, so you'll want that bond to highlight. So you have to really show where it's going. The reason is because it's a computer. Okay, so if you show this lone pair, let's just say I show the arrow doing that. Okay, now it looks like you're moving that lone pair to space. Okay, and that's what it will grade you on. That's what it thinks, because it's a computer. It only knows what you tell it. But if you tell it it's actually moving to the bond, then that'll work. Let me actually pull this up to show you, because it is really important. I don't want you to get really frustrated too much with it. Uh-huh. Homework 1. Let me find one with residence really quick to just show you. Resident. Let's take this through it. Okay, yeah, this is good. Okay, do you see here? This is similar to what we've been doing. Okay, so it gives you one structure, and you want to draw the next one. So let's kind of do this one together. Okay, so let me click on here. And where will can you see this really well, sort of? Okay, there's a negative right there. So where will I start? At the negative, okay? And what can I move on that carbon? The lone pair. So I'm going to grab an arrow here. Now, do you see? Okay, this is going to be really hard. Okay. Do you see right now the lone pair is black? But if I put my cursor over it, maybe you can see it now, it's blue. Maybe. Okay. It is blue. All right, so do you kind of see that it changes? Do you see that kind of flash there, maybe a little bit? Okay, so you want it to be blue because you're telling you want that lone pair to move. Okay? So I'm going to click there, and do you see I'm holding it down right now? And I want to move it where? To the bond. So now the bond is now blue, so that's where I want it. Okay? But this carbon here, how many bonds does it have on it? Well, now it'll have 5, right, if I just left it like that. Is that good? No, something needs to move. Can I move anything over here? No, because it's just a single bond. But can I move something here? Yes, there's a double bond. So do you see how it highlights? It's blue, so I'm going to start right here. Make sure it's highlighted. And it's going to become what? A lone pair. So make sure the oxygen and lone pairs light up. And there you go. Now you can draw the next structure. And this is why I tell you to do that practice part of it. Okay? Because it'll go over stuff like this. Because if you don't practice that, you'll get to this and you're going to have no idea what you missed. Okay? Because you're going to, say you draw, let me get rid of that. Say I have my lone pair and I just kind of drew it. Oh, it's going to move, oops, right there. No. Okay, now it's not even letting me do it. Maybe they changed it. Okay, that might be good. They won't even let you draw it out in space. Okay, you have to tell it where it's going. But let's say you accidentally put it on the carbon instead of the actual bond. Now if I click here, check answer. Okay, it's letting me do it. All right, but usually it will not let you. It's very specific on where it goes. Okay, see, I don't have an X here. This one's correct. And I haven't even done the other one. Okay. And follow the instructions. So it says on here, use the curved arrows. So these are the curved arrows in both structures. Okay. So once you draw this structure, they want you to draw the arrows going backwards, like we've been doing. Okay. And so a lot of times, if you're missing it and you're frustrated and you email me and you're like, I cannot get this number 14, I give up. I'll look and just see that you just didn't draw the arrows on it. You know, something as simple as that, okay? So if you're missing something and you know, swear you have it right, it's probably just something like that, just something in the instructions that you just happen to miss. Okay, you said number 16, right? Let me do this near the end of class because we haven't gone over it yet, but we will go over it today, so it'll be a good one. Let's see if I get to pull up. A good one to do.
And then there was the other one with the resonance on there that I had trouble with. They had, it got into those hexagon shapes where the carbons aren't labeled or whatever.
Oh yeah, we'll go over how to label, or how those are labeled. Let me see. Yeah, let me know if you ever want me to do a problem in class, especially if there's one that a lot of you are having troubles with. Here it is. Label estimate. Probably this one. This one? Okay, so if we're looking at this one, they have both structures and they want you to draw the arrows, okay? Where do we start? With what charge? Negative. There's a negative up here. So I'm just going to show you one of them and then you can figure out the other one. Okay, so let me click on this. So what am I going to move on that negative? A lone pair. So I'm going to move a lone pair from here to become a bond, right? All right. Now this, you can't know what this looks like yet, but all these points here, those are carbons. Okay. So knowing that this is a carbon, how many bonds would that make to that carbon? 5. So I need to move something over. Now let's look here. Do you see in this other structure? This is a double bond here. But what is it over here? Single bond. So I'm going to move this over, and do you see that this is a single bond here, and now it's a double bond. So I'm basically moving that to there. So I grab my other arrow, I move that bond to there. Okay? Now, that would violate this one here. Okay, you can't see the other one. Okay, you don't know how to look at this yet. But just take my word for it. There's 4, so that would make 5. Now let's look over here. This double bond, is it there anymore? So it's single there. No. Where does it move to? Down, right? Yeah. Yeah. And we'll go over that today too. So this bond will move here. Okay? And then our final bond here, do you see our oxygen? How is it connected over here? A single bond, and it becomes a lone pair. So I'm going to move this over to become a lone pair. Okay, so that's what it's looking at there. So sometimes it's good to look at the other structure to see how far they're moving everything over. Okay, without this other structure, that would make it pretty difficult, right? So just compare it bond to bond. So this bond's a single bond here, but over here it's a double bond. So I know I need to move something there. Okay, so just compare the two that way. And you don't fully know how to look at this structure yet, so that's going to make it even harder. But we'll learn that. All right, so let's take a break and meet back here in about 5 minutes-ish. All right, let's start back up. Does somebody have the attendance? Can you pass it around backwards? Okay. So let's practice some more resonance. Exactly. Okay, so let's do this one here. All right, so before we do this, when I told you that resonance stabilizes. So if something doesn't have an octet, you know, like we've seen with we saw this one here. You know, the carbon didn't have the octet, so it makes sense you'd move those electrons down right there to stabilize it in that way. Okay? But sometimes, well, in the past couple ones we've done, everything had an octet. Okay? So that's not what's stabilizing it. What we're going to be looking at for these and the one we did before, stabilization comes from moving these charges around. Okay? So let's think about, we're going to go on this trip, and we're going to go mountain climbing. Okay, and we have to carry a backpack, for whatever reason, of 50 pounds of rocks. Okay? Now, would you get probably very far? Maybe some of you are better shape than I am. I probably would not get very far, right? Backpacking 50 pounds of rocks on my back going out. Okay? But what if you had a friend with you that you could share the load with? Okay? So whenever you get tired, your friend will take it, and then you can walk without the rocks for a little bit, and then they get tired, and you switch back and forth. Okay? Would that journey be a little bit easier? Yes. So the same thing here. So we have like these negative charges on here. You know, like right here. Okay, this negative charge is like our 50 pounds of rocks. Okay? This makes it very reactive. All right? But do you see here? Now it's sharing that charge with nitrogen. Okay, now the charge is over here. Okay, so now it's not as reactive. Okay, so think of it, it's not as heavy as the rocks now. So they can share the charges between oxygen and nitrogen, making both of them not quite as reactive, which is ideal. Okay, everything is going towards stability. Okay, so if you're reactive, you're not stable. Okay, so if you can move the electrons around, which ends up moving the formal charge, you're sharing the charge, stabilizing it. Does that make sense why this happens? Okay, so everything is just stability, really. Okay, so let's look at this. Where would we start on this structure? The negative. And what will we move? Lone pair. To where? The left to make a bond. Will nitrogen like that? No, so if we count how many electrons around it right now, 1, 2, 3, 4, 5, 6, 7, 8. It has the 8, so it doesn't want any more, right? So what can we move? We're going to move the double bond. If I move this, let's say lone pair, if I just move that right there, because maybe you're wondering, why am I going to move the bond versus the lone pair? Okay? If I move the lone pair right there to become a bond, did I change anything? I just added more bonds to it. I didn't do anything. It still has a lot of electrons. But if I actually move this bond away from it, and where do I move it to? Oxygen. So let's put a lone pair on oxygen. Do you see now that bond will be gone? So now it has less electrons. Plus, this oxygen has a positive charge. What's the charge of electrons? Negative. So these electrons want to move towards that positive anyways. Okay, so now let's look at what we just did. Okay, this oxygen right here, how many lone pairs will it have? 2 lone pairs, and it's connected with what bond? Double. Nitrogen, does this still have a lone pair? Yes. What about the bond between these two here? Single. And then how many lone pairs on oxygen? 2. And then did we do anything to this CH3? No, so just leave it. Okay, let's check our formal charges. Oxygen, it did have a negative. What does it have now? 0. It should have 6, and it has 1, 2, 3, 4, 5, 6. Nitrogen, it should have 5, and it has 1, 2, 3, 4, 5. So that's 0. Oxygen, 6, and it has 6, so that formal charge is 0. And we didn't do anything to the CH3, so you don't have to check it. Okay? So which one would be better? The top one or the bottom one? Bottom one. Why? Less charges, right? Less charges means more stable. All right, let's do one more of these. And we'll do more on Monday because I will assume that you will want a review on Monday over the weekend. So all right, is there a negative on here? No. So it makes it a little bit harder where to start. Okay? So let's think about what we can move. Can we move any of our single bonds? No. Do we have any double bonds or triple bonds in here? No, but what do we have? A lone pair. So let's start there. Where do I move it? To the carbon to make a bond right there. So is there any lone pair on nitrogen anymore? No. And let's check our formal charges. Did we do anything to the hydrogens? No, so those stay the same. What about this nitrogen here? It should have 5, but now it has 4, so it gives us a plus charge. Okay, and then the carbon is good. Again, if we wanted to go back to this structure, how would we draw the arrow? From the double bond to the nitrogen lone pair. Okay, so let's move on to another topic. This chapter I feel like is sometimes really random. It has like 500 topics in there and it goes from one to the other. But most of the time in these chapters you're only going to have 2, maybe 3 topics. Yes? Yeah, the first one is preferred only because it has the more electronegative atom with more electrons around it. It would prefer not to have a positive. So basically, your electronegative atom doesn't want a positive, right? It would rather have lone pairs and no positive. Okay, so the next topic they talk about is structures. We've kind of gone over this a little bit. So if I put something, if I draw this, okay, drawing that. This is called the extended or sometimes the full structure. It's essentially the Lewis dot structure. Okay, but what you find is in organic chemistry and pretty much anything in life that we're lazy, right? We don't want to draw the bonds. It gets tedious. So one way to change this, we can do what's called the condensed formula. Okay, the condensed formula is whenever I have, for example, I have carbon. How many hydrogens on that carbon? 3. So I would say H3. Then the next carbon has how many? 2, so CH2. And then the last one, CH3. Okay, so do you see that it's condensed from what you had? And that's why it's called a condensed formula. Okay, and you're just basically not showing all your bonds. Okay, but it still means that this carbon has 3 hydrogens bonded to it like this, 2 and 3. Okay, but we can get even lazier, right? We don't want to show hydrogens because they don't matter. What you'll find in this room that we don't care about hydrogens too much. Okay, how many carbons are there? 3. Okay, so one way to do this is every end and every point will be a carbon. So let me show you. So I have 3. So you put your pen or pencil down, and the point you're making right now is carbon 1. Okay, then I'll go up. That's carbon 2. Go down, carbon 3. Now this continues, so you can, if you had more carbons, say you had 5 carbons, it would be 1, 2, 3, 4, 5. Okay? So you keep going up and down, up and down. And you can see every point and every end. So you count 1, 2, 3, 4, 5. Or in this case, 1, 2, 3. Now that is the whole entire structure there. These 3 represent the same thing. Okay, so let's look at this one further. Okay, so you can see up and down. So you can count, hopefully, the carbons. Just 1, 2, 3. But let's look at the hydrogens. Hydrogens are implied, okay? Unless they actually show a charge on there, that means it's neutral, okay? And what's the magic number for carbon? 4, okay? This carbon right here, if I put a dot, how many lines is coming off of there? 1, right? How many more does it need? 3. So if I draw in tiny, those are 3 hydrogens. And if we see here, what did we have there? 3 hydrogens. Now let's look at this carbon. How many bonds are coming off of it? 2. So how many hidden hydrogens? 2. And then this one right here, there's 1 bond shown. So how many hydrogens? 3. Now we don't ever draw the hydrogens on this. I just want to show you so you can see them. But that's what it stands for. So do you see this one here? All of these carbons are neutral. Do you see I didn't put a plus charge or a negative charge on there? So all of these carbons have 4 bonds to them. And the bonds that you cannot see are your hydrogens. So in your homework you had, I don't remember the exact structure, but let me just draw something like this. right here. Okay, so let's count the carbons. Let's say that's carbon 1. So going around, 1, 2, 3, 4, 5, 6. Okay, so all your points. Do you see, for example, this carbon to this carbon is connected by a double bond? This one to this one is the double bond. This one to this one is a double bond. Okay, so now let's go through. Let's draw our hidden hydrogens in there. Okay, so right here, this carbon at the top here, how many total bonds are coming off of it? 3, because you want to count the double bond. So it has 3, so how many more does it need? 1, so there's 1 hidden hydrogen. This one, same, needs 1 more. Here, 1 more. Here, same. Anyway, all the other ones are the same. So unless it actually has a charge, carbon will always have 4 bonds around it. So I'm going to show you more of these samples on here. Here's some condensed. Another thing to know is that they always show bonds to non-carbon atoms. So here's the extended showing every single bond, right? Now this carbon here, do you see it's a CH3? Okay, so they have CH2. So they have here. And ignore this bromine right now. So we have a CH and then a CH3. Okay? And notice they still show that bond to bromine. So all basically like non-hydrogens or whatever, they'll actually show the bond to them. You see this oxygen right here? You see that it still shows that double bond to the oxygen. Then here's the line formula, which I call skeletal, is what I've always called it. So let's look at this one. How many carbons do we have here? 6, okay? So let's count what we have. 1, 2, 3, 4, 5, 6, okay? Now do you see here, it shows a double bond to the oxygen right there. Because right here you see a double bond oxygen. And then you don't necessarily have to show this hydrogen coming off, but they just happen to. That's not actually necessary. But it is necessary to show the double bond oxygen. So the only thing that you don't have to show is hydrogen. Everything else you do. So if we let's practice another one. Let's do 2 of them, actually. So let's go back and forth. So draw this one in the skeletal form with the lines. And then draw this in a condense. Okay, so looking at this here, how many carbons do we have? 5. That's the first thing I start with. How many carbons? So that means I'm going to draw 5. 1, 2, 3, 4, 5. Now this first carbon here, do you see there's a double bond? So I'm going to draw a double bond right there. Are there any double bonds on these? Or triple or anything there? No, so I leave them. But you see this last carbon at the end? What do we have coming off of that? Double bond oxygen and an OH. So again, it's 1, 2, 3, 4, 5. The first carbon has a double bond, and the last carbon has a double bond OH coming off of it. No, it does not matter. As long as that double bond is connected to that carbon, it can be pointing up, down, left, right. That doesn't matter. Okay, let's look at this one. Okay, this first carbon here would be what? Like a CH3, CH2, CH3. This one would be a CH. You see there's already 3 bonds connected there, so it just needs one more hydrogen. Double bond. And then that double bond is connected to a CH, which is connected to a CH again. Because it has, you see it right here? Do you see the 3 lines coming off of it? So it just needs one more. We'll do this part here in 1 second. We'll come back to that. So let's continue here, which is a CH2. And then coming off of there is a OH. Now, where was it? Right here. Do you see I have, this is called a ring. It's cyclic. Okay? So, coming off right there. What is this first one right here? CH. And it's bonded to a CH2, which is bonded to a CH2, which is bonded to a CH2, which comes back around to the CH. Your cyclics, you have to draw the lines in between them, because if I didn't, if I just put CH2, CH2, CH, CH2, it's kind of confusing what you're trying to say there. Okay? So you always, if it's cyclic, you always connect them with the lines. So you can always tell if something's cyclic. Either it's drawn like this, where do you see it's circular there, it connects back to itself, or it's drawn like this, where you can see the hydrogens, but do you see it's still connected all the way around to itself? Okay, so you'll always be able to tell cyclic. And let me show you more of those here. So these are all called straight chain. Do you see there's no cyclics in any of these? Okay, they're all just carbon bonded to carbon, bonded to carbon with some hydrogens coming off. Okay, let me... More straight chain. Straight chain, it doesn't matter if you have double or triple bonds. As long as it's not cyclic, it's considered a straight chain. Versus over here. Do you see that these are cyclic? Here. So these are some straight chain. But these are connected together in a cyclic formation, connected back to themselves. So do you see how you can tell the difference between them? Okay. So kind of practice with those. We'll do these more in Chapter 3 because we're going to go over how to name them and how to draw them in more detail. But start getting kind of familiar with those. You know, if I drew this for you, do you know what that means? Okay? So in almost every drawing that I do, I typically do the skeletal like this. And right now, you might hate it, but I promise you in like a week or two, it'll be your favorite thing, and you can't ever imagine drawing it like this ever again, okay? Because this is so much faster. All right? So just kind of practice with that, and what you can do if you wanted, you can, cover up the right side with your hand and have this and see if you can draw, the other side. So if I came over here, I was working, I can cover this up. I can see this and see if I can get this answer. Or the other way around. I can start here and, cover up the answer and see after I do it, do I come up with this. Let me show you, there is actually one more thing on here. Parentheses, okay? Parentheses is a way, well, it can mean two things. Usually it means that something is bonded to what it's next to. For example, do you see right here I have CH3, CH2, CH, parentheses OH, CH2, CH2, CH3. Okay? This parentheses means that this OH is coming off of what's to the left of it. Okay? So do you see here? It's bonded to that CH. Kind of like a branch. It's branching off of that CH. And then let me see if I can find another one for you. This one will work. Okay. This is a, you can't see it very well, but it says CH3 parentheses 3 CH. So if I put this over here, CH3 3 CH. Okay? What that tells me is that these CH3s, how many of them are there? 3 of them, and they're all bonded to the CH. So it would look like this if you drew the whole thing out. Like that. Or you could have something like this. So do you see the parentheses right here? Where is that bromine connected to? CH is always the one with the least amount of hydrogens. So you would have like CH3, CH, bromine, CH2, CH3. The other thing that parentheses can stand for, and the only way you're going to see it is with CH2, is this. So if I have CH3, CH2, 4, CH3. Now normally when you see a parentheses, that means it's bonded off of something, okay? The only exception is with CH2. Do you see that CH2 is by itself, okay? And again, this is the only time it ever happens. This actually stands for 4 CH2s in a row. So it'd be like this. CH3, CH2, 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 CH3. So it's basically saying you have 4 of those. Any other thing in parentheses means it's branching off. The one exception is CH2, which just means it's in a line. There's that many CH2s connected together. And I think those are really the two things that come up there. All right, so now the last topic of this chapter is acids and bases. Okay, so there's the Arrhenius definition, and let me just briefly go over that one. Arrhenius, the definition is not as important anymore. So let me just quickly go over it. Basically, a acid, by definition, an Arrhenius acid, will end up creating H3O plus in the product if it's in water. So an acid has to have hydrogen connected to it. You have to have hydrogen on the structure to be an acid. And one way you can tell if something can be acidic, do you see here how the hydrogens are listed first? That's a huge hint that it's going to be acidic. So basically, an Arrhenius acid has a hydrogen connected to it. And then very quickly, a base has hydroxide connected to it, which is OH. So do you see you have NaOH? That has an OH in it, so it's a base. Magnesium hydroxide, so do you see has OH in the formula, so it's a base. Okay? Now, the thing with Arrhenius is not, most things do have a hydrogen to be an acid, okay? But not everything has an OH to be a base, okay? So it's actually a really poor definition. So those are just so you know. Okay, but the big one that we use today would be Bronsted-Lowry. Now, for the definition of an acid, it's pretty much the same thing. You're going to have a hydrogen. Now, what an acid will do you see right here in this reaction? It has it in red, too, which helps. But do you see how the hydrogen's listed first here? But look at NaOH. Do you see that it's listed last? Or basically, it's not first. That means this one is not your acid, but this one is. Okay, so an acid always has hydrogens listed first. That's one way you know it's an acid. Okay, so Bronsted-Lowry says an acid will give up a hydrogen. Okay, so let's look what happens here. I have HCl, which is hydrochloric acid. Now, in the product, it should lose a hydrogen. So I come over here. So here's my chlorine. I come to this side. Is there a hydrogen there connected? No, it lost a hydrogen. Okay? Now, the definition of a base is that it will gain a hydrogen. Okay? So let me actually go to this reaction down here. This is actually a better one to see. So let's look here. Do you see how my hydrogens are listed first here? Are they listed first there? No. So more than likely, this is my acid, but let's check. So according to the definition, it has to lose a hydrogen in the product. So right here, this is H2SO4. But in the product, what is it? HSO4. Do you see that it lost one of its hydrogens? It went from 2 to 1. Do you see that? So it lost a hydrogen, so that confirms it is the acid. So let's look at the base. A base will accept a hydrogen. So right here, it's NH3. But what do I have over here? NH3 plus a hydrogen, which technically makes it NH4. Okay? So that's how you can tell if something's an acid versus a base. Okay? An acid in the product will lose a hydrogen. Okay? That's its role in life. And the base, the only thing it does is gain a hydrogen in the product. Okay? And that's how we define them. These over here are called the conjugate acids or bases. Conjugate just means it's different by a hydrogen. Okay? So for example, H2SO4, its conjugate is HSO4 because they're only different by one hydrogen. And then NH3, its conjugate is NH4 because the structures are only different, again, by one hydrogen. You can always tell the conjugate because it's going to look almost identical to it. Do you see that NH3 does not look like HSO4, right? But it does kind of look like NH4. So those are the conjugate pairs there. So if this is an acid, that means after it's reacted, it's now the conjugate base. we said this one was the base, so after it reacts, it is now the conjugate acid. So they reverse roles there. Let me show you here. Do you see? We have H2SO4 again, and on this side, it turns to HSO4 minus. Okay, so do you see that's the conjugate? Over here it's the acid. So over on the other side would be the conjugate base. And they always reverse roles like that. So if your water is the base, on the other side it's the conjugate acid. And they're always different by one hydrogen. So that's how we define acids and bases. Okay? Hydrogen, or acid loses hydrogen, base gains it. Okay? But what if we don't have the product? What if I just gave you, I covered up the product and you only had these right here, and that's it. Okay? So we need to tell by the structure which one will be the acid, which one will be the base. Okay? One thing you can look at is electronegativity. Okay, so let me explain this. So everything revolves around hydrogen. Either it's accepting a hydrogen or it's donating a hydrogen. Okay, so we need to find what's called the acidic hydrogen. If hydrogen is connected to an electronegative atom, it becomes more acidic. So let's see why. Let's say I have these two. Let's say I just have CH3, CH3 versus CH3, CH2OH. Okay, do you see on here the only hydrogens are connected to carbons? So we're looking at a carbon-hydrogen bond. Now over here, what's the most electronegative atom with a hydrogen? Oxygen, right there. Okay? Now, with electronegative atoms, if I just draw this part right here, if something's electronegative, what is it attracted to? Electrons, right? So these electrons on this bond are being pulled closer to oxygen. So again, remember this is where that polar bond comes in, that dipole moment. This hydrogen-oxygen bond is not shared equally. It's actually more like this. With the hydrogen over here. Maybe a little bond like that. So do you see that hydrogen is already almost gone? Okay? Because oxygens are just trying to steal those electrons away for itself. Okay? So this bond is very weak because oxygen's stealing the bond. Okay? The electrons from it. And so that's why that makes it more acidic. Because an acid, what's its role in life? What does it do? Gives up a hydrogen, okay? So if that bond is weaker, does it make sense it's easier to give up, okay? If you're doing tug-of-war, would you rather do it against a 3-year-old or with a sumo wrestler? The 3-year-old, right, if you want to win, okay? The same thing here. You want that bond to be weak. It's weak because oxygen's pulling that bond away from it, so it's easier to give up. The easier to give up the hydrogen, the more acidic you are. Because by definition, acid gives up a hydrogen. Okay? So our first trend is more electronegative atoms give up a hydrogen easier. Okay? The second trend is size. Okay? So if we look at fluorine versus chlorine. Okay? Fluorine is smaller. And say chlorine is that big, okay? What's in the middle here? Protons, right? So let's say I have a bond. Okay? The closer this bond is to the nucleus, the stronger it is, okay? Do you see if fluorine's really small? Do you see that these electrons are closer to that nucleus? And that nucleus is pulling those bonds towards it, okay? Again, it's just like a magnet. We were looking at, the valence electrons, remember? And we said the outer electrons are easier to pull away because they're further from the nucleus. The same thing here. If you have a larger atom, those valence electrons are further from the nucleus, right? Making them easier to pull away. So if it's easier to pull away, that hydrogen can leave easier, making it more acidic. Okay? So the trend for size, let's say this is the periodic table, this box. Okay? Size, the trend will go down. Down the periodic table, the larger you are. Now, if you're looking at electronegativity, which is the one we just looked at before, that trend goes to the right. Because what's the most electronegative atom? Fluorine, and it's about right here on the periodic table. So the closer you are, the further to the right, the more electronegative you are, which means you're more acidic. And then going down, the size actually makes you more acidic. The last trend, okay, this one can be kind of hard to explain. But let's say I have this acid here. Okay, this is called a carboxylic acid. Now, which hydrogen do I care about? Do I care about these hydrogens or that one? The one on the right, the one with the oxygen, with the electronegative atom. Okay? Now, if I put a base in there, let it react, what does the base do? Takes off the hydrogen, right? So after it reacts, it actually will look like this. Now, I'll explain when we do reactions why all of a sudden I gain a lone pair and a negative charge. Okay? But just take my word for it right now. This is what you get after you react. Okay? Now, do you remember when we did resonance? Okay? Can I move these electrons around? Yeah, I can move. There's my negative. I can move that right there. And then what else would I have to move? The double bond to go up as a lone pair. Now, when I had resonance, did that stabilize something? Did it stabilize? I mean, just like yes or no is all I'm looking for. Yes. Okay? So, do you see that my product, I'm not talking about up here, not the reactant, but the product, if it has resonance, can be stabilized. Okay? I am. But do you see that this negative is now shared between two oxygens versus just one? So anytime you can share a negative charge, even if it's still with another oxygen, it still stabilizes you. Yeah, it pops back and forth, so it shares that negative charge. So anytime you can stabilize your product, that makes your reactant more reactive. I know this sounds weird, but what are we always moving towards? Stability. So if I can make your product stable, then it's more likely to react, right? Maybe? Yes? Okay? So I have this reactant. It's deciding, should I react, should I not? It pops into the future. It sees that it has resonance, can stabilize itself. So it says, okay, I'll do it. Versus, let's look at this one here. CH3. O minus. So this is after it's reacted. Okay, so the hydrogen is gone. Can I stabilize this one with resonance? No, there's no resonance stabilization. So if I'm looking at, look at the original. This acid versus this one, which one would be more acidic? The top one, because it can stabilize the product with resonance. Okay? They both have an OH hydrogen, right? So in that way, they're the same. But the fact that this one can stabilize the product, but this one cannot, makes that one more acidic. Okay? So your acid is always the one that still has the hydrogen still on it. So this is your acid, which makes these the conjugate what? Base. So after it reacts, it becomes the conjugate base. But before it reacts, it is the acid. So the three things we look at, there is electronegativity, size, and resonance. So if we're comparing HCl versus HI. Which one would be more acidic? HI. Why? It's down on the periodic table. So if I ask you these, I'm either going to compare going left to right or up and down. Okay, I'm not going to do a diagonal because those, a lot of times you have to do experimentally. Okay, so HI is more acidic because iodine is a larger size. So do you see comparing? What you're comparing is going down on the periodic table. What about NH4 versus H2O? So now what am I comparing? Am I going up and down or left and right? Left and right? So which one would be more acidic? Which one? The water there. It is more electronegative, but size will trump electronegativity. Because this is electronegative, it's actually pulling that hydrogen. The bond to it is a little bit stronger compared to HI because this is smaller and that's larger. Anyway, so size will always trump electronegativity. Okay, so I never actually got to the pH problem at all. So we'll have to do that on Monday. So I think that's problem, what was it, 16? Okay, so at the beginning of class, we'll go over pH, and then we'll work that problem out, okay, on sapling, number 16.